Okay, so welcome to kind of workshop online class. And as we discussed before, this one is gonna be devoted to step-by-step solution of the games with mixed strategies from the respective exercise set. So we start with S1, and here you've got two players, which are Ravenna, who can choose between safe and risky strategy. Another player is Colin, who can choose between safe and risky as well. And the corresponding payoffs are 4, 4, 1, 4, 4, 1, and 6, 6. Okay, so first you've got the question about the type of this game, and in order to provide the answer, we have to find Nash equilibria, like at least try to find. There is no guarantee they exist. Nash equilibria in pure strategies, and let's check. So if Colin decides to choose safe, then Ravenna should choose safe. If Colin decides to choose risky, again, Ravenna should choose risky. If Ravenna decides to choose safe, then Colin should choose safe. If Ravenna decides to choose risky, Colin should choose risky. Okay, so here we've got two equilibria in pure strategies, and I believe it's visible that here we deal with assurance game. You know, the one when players would like to pursue the same strategy in order to maximize their payoff. And in point B, you're asked to find all the Nash equilibria. And finding all the Nash equilibria basically means that you have to find Nash equilibrium in mixed strategies. Okay, so as you remember, okay, let me just denote to which point it's visible for you. To this one. Okay, great. Okay, so let us start with defining expected payoff function for Ravenna. So for Ravenna, expected payoff function will be depicted as... Okay, first, we have to assign probabilities to possible strategies per each agent. So let's say Ravenna will choose safe with probability P, then she will choose risky with probability 1 minus P. Colin will choose safe with probability Q. Then he will choose risky with probability 1 minus Q. Yeah. Okay, so now we can define expected payoff for Ravenna. And expected payoff for Ravenna can be defined as the sum as expected Ravenna's payoffs associated with each strategy. So, just to simplify mathematical analysis, let's start with safe first. So Ravenna, if she chooses safe with probability P, then, if Colin chooses safe with probability Q, she gets 4. So we have 4Q. Again, if you open the brackets, you will just get P times Q times 4. Then if Colin chooses right with probability minus Q, Ravenna gets 4. 4 times 1 minus Q. So now let's analyze what will happen if Ravenna chooses risky. Then we've got 1 minus P times 1Q, or simply Q, plus 6 times 1 minus Q. Okay, yes, now I believe it's fine. So the next step is to rearrange this function and make it look nicer. So here you've got P, 4Q plus 4 minus 4Q. Here you've got negative p and here positive in front of bracket, so you will have to change the sign. Minus q minus 6 plus 6q. So this entire expression will stand for the value of coefficient of Ravenna's expected payoff function plus the value of intercept will be q plus 6 minus 6q. Ta-da! Finally, yeah, we have to rearrange everything nicely, so you should get p. You just cross it out, 4q minus 4q. So what you should get is 4 minus 6, negative 2, 6q minus q, 5q. So 5q minus 2 plus 6 minus 5q. So keep in mind that q by definition is smaller than 1 because maximum possible value of probability is 1. That's why this part, the value of intercept will be positive. Okay, so once you are done with this part, what you should proceed with is analysis of this function. So I will just rewrite this. Yeah, it's visible. I will just rewrite this. So we've got expected payoff function for Ravenna as p times 5q minus 2 plus 6 minus 5q. Okay, should be fine. So when it comes to the value of coefficient, there are three possible options, yes? So 5q minus 2 can be equal to 0, then q shall be equal to 2 over 5. In this case, there is no relationship between expected payoff for Ravenna and probability p, like probability of choosing a safe option, because again, coefficient will be equal to 0. So the second possible option is that 5q minus 2 is bigger than 0, so we have positive value of coefficient. In this case, the value of q should exceed 2 over 5. And finally, it's possible to have 5q minus 2 less than 0, so we will deal with negative coefficient. In this case, q shall be less than 2 over 5. Okay, I believe this part was clear. So keeping this in mind, you can actually design best response function for Ravenna, where p, the variable under Ravenna's control, probability that she will choose safe, she chooses safe, is the function of q, which is treated as an exogenous parameter and stands for probability that Colin chooses safe. So as you remember, probability takes the value between 0 and 1. So 1 is the maximum possible value of probability. And you've got some critical value of q, which is 2 over 5. I'm not really good in scaling, but if this is 1, this should be 2 over 5. Okay, so if we are located in, this segment where q is less than 2 over 5, then there is a negative relationship between between p and expected payoff for Ravenna, because then the value of this coefficient is negative. And if there is an inverse relationship between p and expected payoff for Ravenna, then as the rational player, Ravenna should keep probability p as low as possible, and the lowest possible value is 0. Okay, when q is equal to 2 over 5, then Ravenna is basically indifferent, It does not really matter which probability she will assign to the safe strategy. It will not affect her expected payoff. So here you have this segment of best response function. And finally, If q is bigger than 2 over 5, so the value of q exceeds this critical value, then there is a positive relationship between p and expected payoff for Ravenna. And if there is a positive relationship between p and expected payoff, in order to maximize expected payoff, Ravenna should keep p as high as possible. And again, as high as possible means 1 in our case, because probability cannot exceed 1. So here we've got best response function for Ravenna. And basically it means that, so this function shows you optimal strategy for Ravenna per each of the strategies undertaken by Colin. Like by definition, of the best response function. So once we are done here with Ravenna, we can do the same kind of analysis for Colin. Again, okay, it's visible and it's visible. Okay, maybe I just can adjust it slightly. Okay, should be fine. So the expected payoff for Colin can be described as Q, probability that Colin will choose safe, times 4p plus 4 times 1 minus p, plus expected payoff from choosing risky. So here we've got 1 minus q. This time we analyze it for Colin. 1 minus q times 1p plus 6 times 1 minus p. Okay, so now again you have to rearrange this. So we put q in front of the bracket. Here you've got 4p plus 4 minus 4p. Again, negative p, because here you've got positive q, here you've got negative q, so you have to change the sign. Negative p minus 6 plus 6p. So as you remember, this will stand for the value of coefficient, and we have to add the value of intercept, which will be 1 times what you have here. So basically p plus 6 minus 6p. Again, now your task is to rearrange everything nicely. So you've got q, again 4p minus 4p. So here you shall get 5p minus 2 plus 6 minus 5p. Again, like here you have symmetric payoffs, so the analysis will be pretty the same. So if p is bigger than 2 over 5, then the value of coefficient is positive. If p is smaller than 2 over 5, then the value of coefficient is negative. And if p is exactly equal to 2 over 5, then the value of coefficient is equal to 0. So in this case, Colin is indifferent because, Q will have no effect on his expected payoff. I mean, this is still an expected payoff function. I mean, this entire function. If p is less than 2 over 5, then there is an inverse relationship between q and Colin's expected payoff. And if p exceeds 2 over 5, then there is a positive relationship. So based on this, since we keep in mind that Colin is a rational player who always attempts to maximize his payoff, we can draw his best response function. So again, q is the variable under Colin's control, and we analyze how it shall depend on p. So again, 1, 1, maximum possible value of probability. Here we've got some critical value, which is 2 over 5. Probably I told you I'm terrible at scaling. So yeah, just assume it's 2 over 5. Okay, so if P is less than 2 over 5, then there is a negative relationship between Q and expected payoff, and rational Colin will keep his Q as low as possible. If P is exactly equal to 2 over 5, then Colin is basically indifferent. Here we have it. And finally, if P exceeds 2 over 5, then there is a positive relationship, and as a rational player, Colin will keep Q as high as possible. So now your task is depict everything, on one function. As you remember, okay, so this was best response function of Ravenna. So until Q reaches 2 over 5, this function goes just along the Q axis. So here we've got the same. Then it goes parallel to P axis, and then it goes parallel to Q axis. Ta-da! Okay, and on this graph, all the Nash equilibria are visible. So here we've got Nash equilibria in pure strategies. So what will happen if two players choose S with 100% probability, S, and equilibrium which occurs when two players choose S with 0% probability, which implies they choose risky with 100% probability. So here you've got equilibrium risky, and here you've got Nash equilibrium in mixed strategies, where both players choose safe with probability 2 over 5 and risky with probability of 3 over 5. Okay, so I believe it was fine. Give me a second so we can proceed to the second exercise. Okay. Okay. So okay, fine. Okay, fine. It's gonna be visible. So here again, in second exercise S2, we have two players, Ravenna, who can choose between up and down, and we have Colin, who can choose between left and right. Okay, so for Ravenna, up, down, Colin, left and right. Okay, looks fine. So the corresponding payoffs are 116, 220, 4, 6, 3, 40. And as we did before, let's start solving with defining Nash equilibria in pure strategies, if there are any. So if Colin goes left, then Ravenna should go down. If Colin goes right, then Ravenna should go up. If Ravenna goes up, Colin should go left. If Ravenna goes down, Colin should go right. So as you can see, there are no Nash equilibria in pure strategies, and our task is to find Nash equilibrium in mixed strategy. Okay, so again, we assume that Ravenna goes up with probability P, down with probability 1 minus P, Colin goes left with probability Q, and right with probability 1 minus Q. So let's start with designing expected payoff for Ravenna. So for Ravenna, expected payoff is gonna be, okay, I will just change the pen. So if Ravenna decides to go up, we have P1 times Q plus 4 times 1 minus Q. If Ravenna decides to go down, we've got 1 minus p times 2 times q plus 3 times 1 minus q. Okay, now technically we are done. We just have to rearrange this function to simplify the analysis. So here we've got p times q plus 4 minus 4q minus 2q minus 3 plus 3q plus the value of intercept, which is 1 times this expression. So basically 2q plus 3 minus 3q. Okay, so what we've got as the result is p times 1 minus 2q plus 3 minus q. Again, this is positive because q by definition is less than 1. It's still visible, it's still visible. Good. Okay, probably I will change anyway. Okay. Fine. Okay, fine. Okay, so for Ravenna, expected payoff is p times 1 minus 2q plus 3 minus q. Again, this is the value of coefficient. So you have, again, three possible options. 1 minus 2q is equal to 0, which means that q is equal to 1 over 2. 1 minus 2q is less than 0, which means that q exceeds 1 over 2. And 1 minus 2q is more than 0, which means that q is less than 1 over 2. So here we have 0 slope, here we have negative slope when it comes to the relationship between expected payoff and p, and here we have positive slope. Okay, so once we are done with this part, let's discuss how Ravenna's best response function should choose like. So again, for Ravenna, p is the variable under control and q is some exogenous parameter. So we have some, okay, so maximum value is 1, 1. So if q with critical value 1 over 2, so if the value of q is less than 1 over 2, we are here, which means that there is negative coefficient next to p. So, you know, increase in probability assigned to up will result in the decrease of expected payoff for Ravenna. So the higher is the probability assigned to up, the smaller is expected payoff for Ravenna. So as the rational player, you know, Ravenna should keep probability as low as possible. Okay, give me a second. Yes. Oh, no, sorry. Yeah, vice versa in this case. I was just wondering, you know, why the solution looks in such a strange way. So yeah, vice versa in this case. So if q is less than 1 over 2, then here we have a positive coefficient, which means that p should be as high as possible. Okay, when it's equal to 1 over 2, then Ravenna is just indifferent. And when q exceeds 1 over 2, so we are here, then there is a negative relationship between p and expected payoff, so it should be as low as possible. So here we have Ravenna's best response function. Okay, now we can try to do the same analysis for Colin. Let me just denote when I should stop here, probably. No, not enough space. Okay, give me a second. Oh, yeah, fine. Okay, so for Colin, expected payoff will be equal to Q times 16P plus 20 times 1 minus P plus 1 minus Q times 6P plus 40 times 1 minus P. Okay, I think I can leave, this part with simple algebraic operations and just proceed to the final result. So once you rearrange this function, you will get Q times 30P minus 10 plus 40 minus 34Q. Yeah, because here you've got 6P plus 40 minus 6 minus 40. Yeah, yeah, looks fine. Okay, so now again, based on this, the value of this coefficient, because this is still expected payoff for Colin, you have three possible options. So first, 30p minus 10 is equal to 0 and p is equal to 1 over 3. 30p minus 10 is more than 0, so p is more than 1 over 3. And finally, 30p minus 10 takes the value below 0, so p should take the value below 1 over 3. Okay, makes sense. So now what you do is you draw best response function for Colin in the same manner as we did it for Ravenna. So now Q is the variable under control and P is some exogenous parameter. The critical value of P is 1 over 3, and the critical value of, probability in general is 1. We know that probability cannot exceed 1. And did I tell you how terrible I am at scaling? So it should be somewhere here, 1 over 3. Okay, so if P is equal to 1 over 3, then Colin is basically indifferent, which Q to choose, because the value of coefficient will be equal to 0, and there is no relationship between the value of Q and the expected payoff for Colin. Okay, if P is below 1 over 3, then actually there is a negative relationship between Q and expected payoff, because again the value of this coefficient will be negative. Okay, so as the rational player, Colin should keep his Q as low as possible. And finally, if P exceeds 1 over 3, so we are located in this space, then there is a positive relationship between the value of Q and expected payoff for Colin, because now this coefficient is positive, and the rational player, Colin, will keep his Q as high as possible. So this is what we get at the final result. Now the fun part. As you remember, here is Ravenna's best response function, drawn based on the same logic. And here you can denote some critical value of Q, which is 1 over 2. And as you remember, until Q reaches 1 over 2, P should be equal to 1 and be parallel to Q. So for Ravenna, until this value is reached, P should be equal to 1 and go parallel to Q. Okay, give me a second. I do not want to mess everything up because I have more than 20 minutes of recording. So yeah, based on this graph, okay, so let's do it in a different way. So between 1 and 1 over 2, this function just goes along the q-axis. So between 1 and 1 over 2, this function just goes along the q-axis. Then it's parallel to p-axis, and then yeah, it goes parallel to q-axis. Yeah, actually, so this is what we should get. Oh, sorry. Yeah, I realized because previously I drawn those two graphs for Ravenna's graph, in the same coordinate where P is on vertical axis, and that's why I just wondering, why I'm doing everything right and still get a different answer. So this is fine. Okay, I hope you understood this logic. So on this graph, you have a single Nash equilibrium in mixed strategies, where P is equal to 1 over 3, and Q is equal to 1 over 2. And there are no other intercepts, which basically reflects the fact that we have no Nash equilibria in pure strategies. Okay, yeah, now it should be fine. Then the next question was about expected payoffs in this equilibrium. So since we know that P is equal to 1 over 3 and Q is equal to 1 over 2, then you can actually just put those values to the expected payoffs, like for instance here. So let's do it for Colin, just for the sake of clarity. Okay, so expected payoff for Colin was equal to Q. In our case, Q is 1 over 2, so we can just put it. So this is 1 over 2 times 1 over 3 times 16 plus 20 times Q, which is 1 over 2 times 1 minus P, which gives you 2 over 3. Plus 1 minus Q, 1 over 2 times 6 times 1 over 3 plus 40 times 1 over 2 times 2 over 3. So yeah, basically here we already have defined, expected payoff function for Colin. Here you have it. Now your task is just put those values, in mixed strategies equilibrium to this function and calculate the result. But I believe that everyone has a calculator, so you shouldn't struggle with this task. Analogously, you do it for Ravenna. Okay, so yeah, okay, that was it. I leave the next task with the chicken game and the one about calculating the value of x. I think it's S5 and S8 for yourself. So please try to do it like using the same method. It will require you to apply some logic and basic knowledge of probability theory. And, like if you struggle completely, please let me know. I will just publish the solutions, without any excessive details like it was in this video. So, yeah, okay. So that's it, and thank you for your attention.